Hello, this is Guillermo Campitelli, and in this video I'm going to present analysis with one variable. So until now I've been explaining the concepts, the rationale behind statistical analysis, and I explained several different approaches. So from now on the explanations will be much shorter. The idea is to apply the previous knowledge into specific situations. So we are going to start with analysis with one variable, and I'm going to present a case study with one nominal variable and then a case study with a numerical variable. And in each of these cases I'm going to use the 7 approaches: 3 parameter estimation approaches, the traditional or frequentist, the Bayesian and the resampling, 2 model comparison approaches, the maximum likelihood and the Bayesian model comparison approach, and 2 hypothesis testing approaches, the null hypothesis testing approach and the Bayesian approach. Okay, so I'm going to also use software to present the analysis. In the cases that I can use for the analysis a simple software like JASP or Jamovi, I'm going to actually show you how to do the analysis. When I use R to do the analysis, I'm not going to show you, but the idea is that you understand how it could be applied if in the future you decide to learn how to use R. Okay, so let's start with one variable, and as I said, one nominal variable. The case study is about voting intentions. We've got a sample of 1,000 participants who answered a simple question: which party would you vote if the elections were today? And they have the option of yellow party, blue party, red party, green party, or they had to indicate whether they were undecided. Right, so we've got the data, and we are going to use the software JASP to analyze the data, and these are the things that we are going to do to get the descriptive statistics. Okay, so bring in JASP. And basically the first thing to do is to open the data set, and the data set should be saved into CSV format. So CSV format you get when you work in Excel, but instead of saving the file as an Excel file, you save it as an CSV file. So simply you go to File, and here you can you will have recently used files. So if you use one file that is there and you want to use it again, it's going to be there. There are examples that JASP provides that you can use. You can use the OSF, the Open Science Framework. So if you log into your account, you can access to data sets that other researchers make available for free, or you can use your computer, some data set you saved in your computer, and that's what I'm going to do. So basically it gives you the option of recent folders. I've been working on these, so the folder is here, but otherwise you go browse, and basically you're browsing in your computer. So I'm going to go to chapter 8 folder, and voting preference is the file. You can see that it looks like an Excel file, but it says Microsoft Excel comma separated values, so CSV file. Okay, you open it, and basically in the first column we have the participant number from 1 to 1,000. The preference is the party that they chose, and sometimes in some analysis you may need to code the nominal values into numbers. So I added this column, but I don't think we are going to use it for our analysis. Okay, so the first analysis is the descriptives. You go to descriptives and descriptive statistics. Okay, so JASP gets ready to prepare a table, and the interesting thing here is that everything that is here, it's APA formatted. So you can basically copy and paste it in your Word document, and you've got the file ready to publish. Okay, so what you need to do is to drag. I can drag it to the variables file, the variable preference, or I can just select and use the arrow. Same if I don't want the variable there. Okay, so we've got the variable preference, and we tick display frequency tables. That only works for nominal and ordinal variables, not for numerical. Okay, and I've got the frequency table, and which is very useful, and we can, as I said, copy and paste it in a Word document. So basically it tells us for each of the categories what's the frequency or count, and the percentage. If you divide percentage by 100, you get the proportion. Okay, so basically that's a useful piece of information. Now, if we want to do another analysis, we can just we press here. So you click on that side, and the old analysis appears there. Okay, so now let's do some plots. So we go to plots, and we tick display distribution plots. So here it did it immediately. That's why I like JASP. You do something here and it immediately appears there. Now I'm going to show you a bit nicer plot than this one, but this is perfectly okay plot. Now that's all we need. Statistics, they would be useful for the numerical variables. So for the nominal variable, that's it. So let's show in the slide. So I did a bit nicer a graph here, but the same idea. It's the same graph as the one that JASP would do for you. Okay, so now let's start with the 7 approaches. First, the parameter estimation approaches. We start with the traditional or frequentist approach, then the Bayesian, and then resampling. Okay, so for the traditional parameter estimation, I'm going to use JASP as well. And we need to, one of the things you have to understand about the statistical software is that they are typically biased towards doing either model comparison or statistical significance testing, null hypothesis testing. And so here we want to do parameter estimation, so we will have to use some tricks in order to be able to do it. So what we are going to do is we are going to ask JASP to do a binomial test, and that's the way it will work. Okay, so basically once you did your descriptives, now we go to frequencies, because that's what we have. We've got frequencies. The graph here shows you frequency or counts. Okay, so an analysis of frequencies. We are going to do the binomial test. We are not going to go Bayesian yet, because we are within the traditional approach at the moment. So binomial test, and again we put preference. And now here it's important, the test value. So we want to test for each proportion. Okay, sorry. No, we don't have to worry about the test value just yet, because this is about the test value is hypothesis testing. So at the moment we are not interested in this. So what we want to do is an estimation of the proportion of blue preferences, green preferences, red preferences, or yellow preferences and undecided in the population. So what you need to do is to tick confidence interval, and so basically that gives us here the confidence interval. So basically our point estimate of the proportion of people voting for the blue party or expressing preferences for the blue party is 0.186, and the confidence of our estimation is expressed in the 95% confidence interval. So basically it is between 0.162 and 0.212. So typically this is a good, it's not a very wide interval, so it's a relatively good estimation, but because it seems that the parties are very tight, this will not give a very good indication of who is going to win the elections. But in other cases, when the differences are higher, then this interval will be enough to predict the winner of an election. Okay, so basically that's what we do in the parameter estimation. We've got one point estimate for each proportion and one confidence estimate, interval estimate, which is typically the 95% confidence interval. Now we can have plots, descriptive plots, and here it shows the proportion in the dot and with the confidence interval, these little bars. And so this one goes from 0 to 1, and the 0.5 is because that's the test value, but we are not paying attention to that just yet. Not very useful, these plots, but we can there is an option you have. Okay, so let's return to the slides, and here is the a table that presents the information I just showed you in JASP. Okay, so now let's move to Bayesian parameter estimation, and some aspects I'm going to use the software R, which I'm not going to show you, and in when possible I'm going to use JASP. Okay, so Bayesian parameter estimation, it always involves defining a prior. So here what we want to estimate are 5 proportions in a population. So we call them pi to each of those proportions. And we have a prior distribution, which is, as you can see, for all, so for each pi, let's say pi yellow, we have what we call an informative prior. So we are saying we've no idea what to expect about pi yellow, so we just decide that we put for each possible value of pi, we give the same probability. That's before seeing the data. So this is a uniform distribution, but remember that we like to use a beta distribution, and if beta distribution has parameter a equals 1 and b equals 1, we get this uniform distribution. Okay, so that's the priors. Then the second aspect of parameter estimation, Bayesian parameter estimation, is to have a distribution to determine the probability of the data. So we are going to use the binomial distribution. Remember, the binomial distribution has parameter n, and in this case is 1000, and it has a parameter which is called probability, which is called pi as well. And in this case we are going to use a pi, the pi for each preference. So basically here gives you an example. So in order to determine the probability to obtain a specific count of yellow, given a specific parameter pi yellow and k background knowledge, we're going to use a binomial distribution with n equals 1000 and all the possible values of pi yellow. Okay, basically what we are trying to say is, in these 1000 observations that we have in our sample, what's the probability of observing 1 out of 1000 that preferences of yellow? Given that in the population the proportion of yellow supporters is a certain amount. Okay, so let's say the proportion of people in the population that supports the yellow party is 0.2 or 20%. Okay, so if that is the case, then the most likely count we will find in our sample, because we don't have the whole population, we've got a sample, so we are not going to get exactly 200 out of 1000, which is 20%. It is the most likely value is 200, but if we get 199 or 201 or even 198, 202, it is still very likely. Now you go further away from 200 and it's less likely. And in order to express that, we need a distribution. The binomial distribution is the perfect distribution to do that. So basically it will say if the pi yellow is 0.2, then the probability of obtaining 200 is the highest and other values is lower. And we do the same for all the 5 categories. So let's say, for example, that we consider the pi blue in the population is 0.3. So 30% of people supports blue in the population. Okay, but in our sample of 1000, how many blue we expect? Well, the most likely value is 300, but values 301, 302, 303 are still very likely, same as 299, 298, 297. And the further away you go from 300, the less likely is to find that value. Now, but remember also that in Bayesian statistics, we consider all possible parameters, or all possible parameters that we determine in the prior. And remember that we chose a prior in which we say that any value from 0 to 1 is possible, and they have the same plausibility. So basically, we have to consider for pi equals 0.01, what is the probability of obtaining 0 blues, 1 blue, 2 blues, 100 blues, 300 blues, 1000 blues, and so on and so forth. So we need for each value of pi to determine each count, each possible value of the sample, each possible value of the preference for blue in the sample. Okay, so we need one of these distributions for each category. Now, then we have the prior, and we've got the distribution for determining the probability of the data. So when we combine these two, we obtain the posterior distribution. And so basically now in the previous explanation, we didn't know what the count of yellows we would find in our sample, but now we know it's 204. So of the 1,000 people, 204 said they would vote for the yellow party. So this is the posterior. What's the probability of each value of pi yellow, given that the count of yellow in our sample was 204, and always remember background knowledge. Okay, that is equal to the probability of obtaining 204 given each parameter value or each pi value, which is what I just showed before, the probability of the data given a parameter. And that multiplies by the prior, but remember that we gave a 1 for each possible value, so this wouldn't be important because we were multiplying by 1. And then we divide that by the probability of obtaining 204, and that's regardless of the parameter values. So if we take into account all possible parameter values, what is the probability of obtaining the 204? When we do that formula, we come up with a distribution. So because we get a probability for each value of pi yellow. So here, that's each value of pi yellow has a probability. And we are talking about probability density because it's a continuous variable, no probability mass. Okay, so for pi yellow, we see that the most likely value is around 0.204, and values that are further away from that are less likely. So basically, we can say that we are pretty sure that in the population, the proportion of supporters for the yellow party is between 0.16 and 0.24. Let's see if that we can be more precise. And here are the summaries for all the posterior distributions. Okay, so for pi yellow, the mean of that distribution is 0.205, and the 95% confidence interval is between 0.18 and 0.23. So basically, we are saying is that we are 95% confident that in the population, the proportion of people supporting the yellow party is between 18% and 23%. Now, remember that when I talked about confidence intervals in the traditional approach, I cannot say I'm 95% confident, because the confidence intervals in the traditional approach don't allow you to say that. So the Bayesian approach, we add a bit of complexity, makes it a bit more difficult to run the analysis, but now we are able to say more things. So now we are perfectly okay to say that we are 95% confident that the values of the proportion of people supporting the yellow party are between these two values. So that's why the Bayesian approach is important. Okay, for the proportion of people supporting blue in the population, that distribution, which I'm not showing, the mean is 187, and the interval is from 1.163 to 0.211, and you've got the values for all the categories. Now, as I said, JASP is is designed to do hypothesis testing or model comparison, but typically not very good to do estimation. But there, in some cases, JASP produces these really nice graphs in which they show you the prior distribution and the posterior distribution. So the way I got this graph from JASP is to use the binomial test. Now, we don't want to do the binomial test, but I told you that it's a trick that we have to use to get parameter estimation. So we go to the Bayesian binomial test now, and we put preference over there. Now the test value, you can put anything. I think you don't go over 0.7, but values there, you can put anything because we are not testing. But here, put a tick prior and posterior, so we get this graph. Okay, so that's what we get. And again, if you click there, you can copy and paste the graph. And actually, if you do this, you can save it as an image. So that's what I did, and I copied it here. Okay, so basically, it's an interesting graph that shows you there the confidence interval. That's for yellow. You see the pi of yellow, 0.18 to 0.23. The confidence interval is there. It shows you the prior, which is a beta with A1 and B1. So it's a uniform prior, and it shows you the posterior, which is here. The other pieces of information are not important for parameter estimation, but we are going to see them when we see model comparison or hypothesis testing. But here you've got the difference between the prior and the posterior. So we started with giving equal plausibility to all values, and now we've got a very strong plausibility for values close to 0.205. Okay, now let's go to resampling. So parameter estimation with resampling, and I did this all with R. So in this case, I'm not going to show you the analysis, but basically what you need to do is from the sample of 1000 preferences. So we've got the 1000 values, and we obtain a new sample of 1000 preferences by resampling with replacement. So from those 1000 values, which will say yellow, blue, green, red, undecided, okay, by chance, by randomly choose one value, and we write that down. We put that value back into the 1000 values, and again randomly choose another value, and we write that down, and we do it 1000 times. So we've got a sample of 1000 preferences, which we obtain by resampling the values that we already have. So we are not using a theoretical distribution. So in that sample, the proportion we record what's the proportion of yellow, what's the proportion of blue, what's the proportion of red, what's the proportion of green, and what's the proportion of undecided. And we repeat that process thousands of times. Let's say 5,000 times. So basically we have 5,000 proportions for yellow, 5,000 proportions for blue, red, green, undecided. So, and we put that in a histogram. So we need 5 histograms, one per each of the pies, and it gives us a distribution. So here is the example of pie yellow. The values are similar to the previous approaches, not exactly the same, but as you can see, values close to 0.2 are more likely. Okay, so here we've got the means of these distributions. So for the pie yellow and for the others. So pi yellow mean is 0.186, and the confidence interval is 0.162 to 0.210, and we've got for all the categories the same information. Okay, so this finishes the first video. In the next I'm finishing parameter estimation. In the next video, I'm going to explain model comparison and hypothesis testing of the same case.